All right, so in section 1.2, you pretty much know this already from what we've talked about in class, but just some definitions, like always. A non-zero row or column is a row with, you know, like this down here, like this is a zero row. So this is a non-zero row. This is a non-zero column. So it has to have at least one number in it. A leading entry. A leading entry is like the first non-zero number. So like this is a leading entry in here. That one's a leading entry. This one's a leading entry. That one right there. Okay. So something is said to be in echelon form or row echelon form if it has these three properties. So I'm going to talk about these down here. All non-zero rows are above all non-zero rows are above any row of all zeros. So like this, so any rows with all zeros are at the bottom, basically. All right, each leading entry of a row is in a column to the right of a leading entry of the row above it. So like here, so like if this has a leading entry, the next column, the leading entry has to be after that, right? So it has to be here, or in this case, it's there. So like letter B breaks that rule because this leading entry, then you got that one, that's okay, but this right here, so this breaks. This is not in row echelon form or echelon form. So, but if you did switch these two rows, then you would be like, oh yeah, then it is. So this is in neither. This right here is in, over here is in row echelon form, okay? And then this one back here, and this last one, all entries in a column below a leading entry are zero. So basically, you know, you got zeros under here. And so this right here, whenever you have zeros below a leading entry and zeros above it, zeros below and zeros above it, that's actually called reduced row echelon form. And that's what you're going for, you know, or on a calculator. But anyway, all right, so some important terms. You're going to have a pivot position. All right, and also back here, each matrix is row equivalent to only one reduced row echelon or reduced echelon matrix. So that means if I do some row operations and you do some row operations, we should come to the same final result in reduced row echelon form. Okay. All right, so important terms, pivot position. So pivot position is basically your first item in the row, first non-zero item, that's called a pivot. So there's a pivot right there, there's a pivot right here, here's a pivot spot. So a pivot position causes you to get a pivot column, right? So like this is a pivot column, that's a pivot column. All right, and the pivot is just a non-zero number that is in the pivot position. Okay, so what's going to happen is you're going to reduce everything. So this is this one reduced. And so you can't really tell where the pivot positions are looking at a matrix that's unreduced. So you get down here. So these are all pivots. But you can, like, let's say that this right here, let's say that this was a augmented matrix. So you got x1, this is x2, x3, and x4. So look what's going to happen here. I have 1, 2, 3 pivots, and I don't have a pivot in this column here. So that's going to be something called a free variable eventually. So when your variable doesn't have a pivot spot, there's no pivot column in that one, then that's going to be something special later. Okay. All right, so let's go to the next one here. So let's see, circle with pivot positions. So we're just going to go ahead and do a couple reductions here, or row operations. So I'm going to do -3 times row 1 and add it to row 2 for that guy to try to get rid of that 3. Then I'm going to do -5 times row 1 and add it to row 3. All right, so that's going to give me 1, 3, 5, and 7. That's going to be a 0. Then I'm going to get -9 plus 5, so -4. Then I'm -9 plus 5, yep. Then I'm going to get -15 plus 7, so -8. Then I'm going to get -21 plus 9, so -12. Right here, this is gone. I'm going to have -15 plus 7, so -8. Then I'm going to get -16 and -34. Okay. All right. So looking here, I think you know what I'm going to do. I'm going to divide this all by -4. I'm going to divide these by, looks like they all divide by -2. All right, so 1, 3, 5, 7, just to make them a little bit more manageable. 0, 1, 2, 3, and 0, let's give me a 4, an 8, and a 17. Okay, so now I'm going to do negative 4 times row 2 and add it with row 3. Okay, so that way this will go away. So I got 1, 3, 5, and 7, 0, 1, 2, 3, and 0. This will be 0. This will be 0. And this guy right here, that'll be negative 12 plus 17, so 5, right? And so basically I can tell you now I'm going to have 3 pivot columns, okay? Now if this was an augmented matrix, like if I had an augmentation right here, remember that would be a no solution because a bunch of zeros multiplied by their variables can add up to 5. But, you know, for now that's not what I was being asked. So, all right, so use row reduction to solve this. So we've done this quite a bit before. Why don't I just show you? I'm just going to skip this one actually. So I would just end up, oh, maybe not. I'll just do it. You can skip ahead if you want. So 1, 1, 2, negative 1, negative 1, 0, 2, and negative 3. I got 0x1, 1 for x2, 2 for x3, and negative 2. I got 2, negative 1, 1, and 1. So basically, you know, I have 4 equations, but only 3 variables. One of these equations is going to go away. I don't need 4 equations for 3 variables. So let's see what happens. Let me add these two. Row 1 plus row 2. Let me do negative 2 times row 1 plus row 4. All right. So 1, 1, 2, negative 1. Add these, 0, 1, 4, and negative 4. All right, this one, 0, 1, 2, and negative 2. So see that right there? That's just a copy. This is just 2 times this one. So I'm going to just, those are all going to cancel out. Let's see. That adds up to 0. Negative 2 plus negative 1 is negative 3. Negative 4 plus 1 is negative 3. And then, let's see. It's going to give me 2 plus 1, so 2 plus 1 is 3. Okay. All right. Let me check this out for a second. So I'm just going to say that these are all zeros here because they will cancel out with those. But I'm worried about, oh, no, it's fine. Never mind. All right, so let's divide this row by 3, so, or negative 3. So I'm going to get 1, 1, and negative 1. Okay. All right, here we go. So 1, 1, 2, negative 1, 0, 1, 4, and negative 4. I'm going to put this one next, 0, 1, 1, negative 1. And the last one, you know, all zeros. So a lot of times, you know, you can just like drop that away. Like, you don't really need to write all this. All right, so let's work on this guy. So let's do negative row 2 plus row 3 to get rid of that guy. So I got 1, 1, 2, negative 1, 0, 1, 4, negative 4, 0, negative plus that is 0, negative 4 plus 1 is negative 3. This will be 4 plus negative 1. 4 plus negative 1 is 3. All right. So now I can divide this one by negative 3 and tell you that this turns into a 1 and this turns into a negative 1. So there's my answer. I got x3, basically. x3 equals negative 1. So then put it back in here. You know, x2 plus 4 x3s, so 4 times negative 1 equals negative 4. So that's going to be x2, I'm going to add 4 over, is 0. So if you then plug it back into any one of these, you're going to get that x1 is 1. So 1, 0, negative 1. Okay, so that would be your solution. Okay, but, you know, one of the rows went away, we didn't need it. All right, last little bit right here. So notice in this problem, number 4, I don't have enough rows to get a definite answer. If I have 3 variables and only 2 equations, only best I can hope for a solution is infinite solutions. So I got 1, negative, oops, I got 1, negative 1, 3, and 0, 2, 1, 3, and 0. All right, oh, that was ugly. So let's multiply -2 times row 1 and add it to row 2, right there. All right, so 1, -1, 3, and 0. And -2 plus 2 is 0. This is going to be 2 plus 1 is 3. This is going to be -6 plus 3, so -3. And these are all just zeros. All right, so I'm going to divide this by -3, and I'm going to get, just by 3, and just get 1 and -1. All right, so I have left here 1, -1, 3, and 0. All right, I have 0, 1, -1, and 0. So I have 2 pivots. So that means that x1 and x2 are going to be explicitly defined. But this one right here, this is called a free variable, okay? So that means that x3 is free to be whatever he wants to be. So x3 is equal to x3. You can write x3 equals free, or just x3 equals x3. That just means you're going to pick x3. So then this equation is telling you that x2 minus x3 equals 0. So you're going to say x2 is equal to x3. That doesn't always happen, but x2 equals x3. And then this equation is telling you that x1 minus x2 plus 3x3s equals 0. So x1 is equal to x2 minus 3x3s. So x1 equals x2 minus 3x3s. So that's your solution. So if I pick an answer that follows these rules, so let's do it. Let's pick a number for x3, like 2. So if I say a 2 here, x2 is also 2. And then down here, I'll be doing 2 minus 3 times 2. So 2 minus 6 is -4. So this is a solution to that system. If I put these numbers in, it works. So if I put a -4 minus 2, that's -6, plus 3 times 2, 6 is 0. Here, if I get -8 plus 2 plus 6, that gives me 0. So it makes numbers that make the equations true, right? That solve the equations, or that are solutions, all right? So, but it has to follow this pattern. And yes, you could also do this. Since x2 and x3 are the same thing, you could just say that x1 is equal to 1x3 minus 3x3, so -2x3. So you could also replace this with that if you wanted to, but I'll just leave it. All right, so that's what this is. Yeah, never mind. All right, so we basically have this answer kind of problem here. This is an augmented matrix. You notice I have pivot columns. I don't have enough pivot columns to cover every column, so I'm going to have infinite solutions. So I notice that if I don't have a pivot column, so pivot columns are 1, 3, and 5, my basic variables are going to be where the pivot columns are. So x1, x3, and x5. But my free variables are x2, x4, because there's no pivot. Okay, so x2 and x4. Okay, so basically, you got these equations. You also have that x2 equals x2 and x4 equals x4. Okay, so these basically turn into that. Okay, down there. All right, so this is just going to be a general solution, right? And so remember, this means infinite solutions because you can pick anything for these two numbers, and then everybody else depends on that. Okay. All right, this right here. So these are all augmented matrices. My question is this system consistent or inconsistent? And is the solution unique? So remember, if the solution is unique, that means there's one specific answer. Infinite solutions is not unique. All right, so if this was augmented here, having a pivot spot in the last column in your augmented column is mean there's no solution. So no solution is inconsistent. Okay. Over here, all right, I got definite ones right here. This just means that x2 equals 0. So there is going to be one solution, and it's going to be unique and consistent. Okay. All right, if this is my pivot column, I'm getting like nice, pretty answers. x3 equals 2. I could use that here to get x2, and so this is consistent and unique. over here. I basically don't need this last row. I'm getting that x2 is 3, x1 is -5, so again, consistent and unique. Okay. All right, so consistent if the rightmost column is not a pivot column, so that's what we're talking about there. And the last little bit here, consistent. If you're consistent, then you either have a unique solution or you have infinite solutions, right? So you have to have a free variable. All right, these down here, these are systems, so these are augmented. So this means, look, I got x3 is free. So x3 is equal to x3, but x2 is 4, and x1 is -9. So this is still an infinite solutions. These two are staying stable, but this one is anything it wants to be. This is augmented. I got x1, x2, x3, and x4. So I got 2 pivots there. That means that x2 and x4 are free. x4 is x4. X3 is, if I bring this -2 over, now if you want to, you can write, x3 or minus 2x4 equals -3 if it helps you to solve it. But move this over. So I got 2x4s minus 3. All right. So this guy here, I'm going to have for x1, I'm going to have 7x2s, so positive 7x2s, no x3s, minus 6x4, and then plus 5. And you can put in any order, but there we go. That's infinite solutions. All right, with these little questions down here, I always like to make a little picture. So a 4x6 matrix. I have 4 rows, all right, and 6 columns. 1, 2, 3, 4, 5, 6. What's the largest possible number of pivots? So, I can have a pivot in every leading spot. So there's going to be a leading spot here, 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 and here. So I'm only going to have 4 pivots. Okay. All right, what's the largest possible number of pivots in a 6x4? So 6 rows and 4 columns. But still, look, pivot, 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 pivot. So still 4. So basically, the number of pivots that you can possibly have in a matrix follows the smaller number, the rows or the columns. All right, how many solutions does a consistent linear system of 3 equations and 4 unknowns? So you have too many you have too many variables and you don't have enough equations to cover them. So if your system's consistent, then it's going to have infinite solutions. That's the best you could hope for, because there is a free variable. Right? Suppose the coefficient matrix corresponding to a linear system is 4x6. So you got a 4x6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. That's just your coefficients. So then you have your answers over here. It has 3 pivots. All right. How many pivot columns does the augmented matrix have if the linear system is inconsistent? So if this has 3 pivots, so like here and here, it would have free variables. So if you wanted to have inconsistent, then you'd have to have another pivot over here. So it'd have to be 4, because you'd have to have a pivot in your answer column to be inconsistent. All right, and that'll do it. Bye-bye.